see how we can use this to distinguish two surfaces. So we measured surfaces made by fused deposition modeling. So this is where we lay down a semi-solid polymer, and we hope that they stick together, and we keep just putting them down. One of the interesting things is we note that this is almost a reflection of a machine surface. So the machine surface has got relatively sharp little ridges, and this has got relatively sharp little valleys. So caution, this is going to be more susceptible to fatigue. But as we lay these down at different thicknesses, here we're comparing two different thicknesses in the relative areas on several measurements. So we can do some statistics. At the large scales, we're getting about the same thing. And so they're kind of overlapping. But then at some scale, they're clearly distinguishable by their relative area. So here, multi-scale, there's a whole bunch of scales. We're calculating the relative area at scales, and we can take a look at each scale and see, what's going on here. So, so we don't have to do filtering. Now, my friend, Professor Bigorel from Valenciennes in France, points out that this is essentially a low-pass filter. So if I have a large bump at a high scale, the increase in relative area from that stays with us all the way through to the finest scales. So here are the same two surfaces, and here we're looking at the complexity. Now the complexity is the local slope on the area scale filter. So this is similar to a fractal dimension, and this is more like a bandpass filter because the slope is not influenced by what's happening out here, unlike the relative area. So we see a different kind of result here, just telling us about the irregularity of the surface in that neighborhood of scale, essentially. Now, we can calculate the mean square ratio. So this is an F test. This is a test for statistical discrimination. And the mean square ratio has limits that tell us how confident our discrimination is. So if we want to discriminate with 99.9% confidence, meaning that we would be able to distinguish these surfaces 999 times out of 1,000 if we did a similar test. Here, right here, now there we're going to be doing better because this is the cutoff limit. But this is scales where these surfaces can be discriminated. And here are the scales where they cannot be discriminated with this level of confidence. So, and if we remember right, we had a certain amount of overlapping here. And now we are seeing the how we can discriminate. Here's another example. The previous one was done at WPI. And so this one was done in Sweden by some friends there. And they're looking at complexity and the scale bullet, and they're trying to distinguish milling and hammering of surfaces. So hammering is like a kind of shot peening effect to impart, for example, a residual compressive stress. And how are the surfaces different in terms of their roughness? So we're able to identify a scale below which you can tell how the hammering has modified the milled surface. Here's another example using a multi-scale analysis. And this is a slightly different kind of analysis. And it's made for CT scans. So here is computer tomography result from a measurement. And these are, we're looking at here comparing three different structures in a multi-scale sense. So here's how and he calls it the relative internal area. And this was Jan Cuisenet who did this at the ENS Cachan at the time. And this is one of their top engineering schools where many of the professors, engineering professors in France, get trained. And so we can see these three different patterns of building additive structures are distinctly different, and their ranking changes at a certain scale. So right here, they're not distinguishable, but the rank that you have here is the opposite of the rank that you have out here.